Okay, so we're working on the function sine of nx. And to give you a picture, there's a little Desmos here that will help us out. But to give the little picture, in case you didn't have it in your head, sine of nx looks like this. So they're squiggles, and they go between -1 and 1. And the bigger n is, the more squiggles there are, the more dense they are. If you're a physics person, n is like the frequency. It's like how many squiggles. Oh, yeah, actually, it's the angular. There's this like frequency in degrees versus frequency in radians. N is exactly the frequency in radians. But that's what it looks like. Okay, so what are these things doing? Let's see what you guys said. Okay, so two people said it goes to 0 in R, and actually it is always equal to a number, but that number is not 0. Did anybody see what the norm is? Yeah.
It's pi.
It's pi. Yeah, this is what we did on the first day. So if you square these functions, oh no, now I've lost my Desmos. Okay, here it is. So if you square these functions, so they go up, down, up, down, up, down. They're positive and negative. But if you square them, they're always positive. We can draw a little picture of that actually. Why don't we square it? Square it. So there they are squared. To do the L2 norm, you have to square the function. And then they're always between 0 and 1. So the top of the peak is at 1. 1 squared is 1. And the bottom of the peak is at 0. 0 squared is 0. So they're kind of between 0 and 1. And by that sine squared plus cosine squared equals 1 trick, they are about half the time. Their average value is exactly a half. And so the total integral is the half. Their average height is a half. So the total integral is a half times the width, which is 2 pi. So actually the norm is equal to pi exactly. So we're working on the function sine of nx, and the norm in L2 of sine of nx in L2. Well, the norm squared is equal to pi, and let me say it like this, the integral from minus pi to pi of sine squared of nx dx. The average value is a half, and the length of the interval is 2 pi. So the norm squared is pi, and therefore the norm of sine of nx is always square root of pi, because the norm squared is pi. But this is all in L2, of minus pi to pi. So very good. So it's not going to 0. Almost everybody got that. Okay. Really should have these open in the same tab, but okay. Similarly, only one person said it goes to 0 strongly. Actually, these two statements are the same, because what does strong convergence mean? So this 0 on this right-hand side is not the 0 the number, it's a 0 the function. And how do you tell if some functions are converging to another function? You take the difference of the functions, and you take their norm. So fn to 0 strongly means, or just to any f, really, f means fn minus f in norm is going to 0. And so if you were going to subtract something, could you subtract something and make it go to 0? Well, certainly subtracting 0 is not going to work, because the norm is always square root of pi. So that one's definitely wrong. So people got those right. The one, 9 out of 12 people said it's going to 0 weakly, and 3 out of 12 people said none. So it's either one of these two. Either it's going to 0 weakly, or it is none. You guys voted 9-3, and you are correct. So people who chose that it's going to 0 weakly are right, and we're going to see by the end of the class, we're going to have a nice little proof of why it's going to 0 weakly. Does anyone have some nice intuition of why it's going to 0 weakly? Maybe this was mentioned last class or something. Or what? Of the 9 people, why did you guys think that is true? Yeah.
Does it relate to orthonormal?
It does relate to orthogonal, and we're going to see that if you have an infinite orthogonal system, then it has to go to 0 weakly. So it is true, because they are orthogonal, it will be a true fact, and we are going to prove that.
Oh.
But is there a simpler way to see what's going on? Why is it when you add more wiggles, it's going to 0? Yeah?
I was thinking about it as if you squish like infinitely many wiggles, there'll be the same amount. There'll be infinity on both sides of the...
This is beautiful. This is like this sounds silly, but this is like at least how mathematics works in my head. You come up with a silly idea, like infinitely many wiggles on top, infinitely many wiggles on the bottom, and then you make it rigorous. And this is totally what's happening. So here's the like picture proof of what's going on that I put together for you, and it's exactly this infinitely many wiggles idea. So first of all, let's get rid of the square. Okay, and let's test it against some function. So weak convergence means you take the function you're looking at, sine of nx, you multiply it, or more generally, take the inner product, but the inner product in L2 is multiplying. So here is some other function f in purple. So this is some other function. You can think of these as like a test function. Like we're testing the function sine of nx by taking the inner product against this thing. So let's write this down, just so we can think of what's going on. So to check a weak convergence, you do the sine of nx, this function, against some function f of x for some fixed function f, and we want to check that this goes to 0. Check that. And you can think of this, if this was like R2, you would have like two directions. We're working in L2, so there's infinitely many directions. There's infinitely many functions f you can put in. I just put in some example over here of this purple guy. Let's see what happens when we multiply them. And I called this multiplication G. So here it is. G is the multiplication of the purple function, and the orange function is the blue function. And you can see the squiggles get either big or small, depending on what's going on. But as you increase n, so if you start with just a few, maybe I'll make this a little bit slower. So if there's only 2, if n equals 2, and there's only a couple of squiggles in the orange, then you have these really big squiggles under the blue function, right? And then when you go to do the integral, which is over here, you get some number. Here it's 4.71. And you can visualize that by looking at the area above and the area below, right? So in this case, there's lots of area above and one big area below. They sort of cancel out a little bit, but at the end of the day, you have an integral of 4. But what happens as you increase the number of squiggles? Like, see if you can imagine in your head. So as you increase them, you have lots of up-down squiggles, up, down, up, down, up, down. And the idea is, on any part of the function, it's sort of like flat-ish, you have a bunch of, as long as you're squiggling faster than the purple function is squiggling, then you have infinitely many squiggles, and you have ups and downs, and they sort of cancel out, right? So as you increase this thing, you're hoping that the greens and the reds here are almost exactly balanced because they're oscillating so much faster than the purple function is moving. So when you go from one to the next one, they haven't changed height very much. And hopefully, if we go down the integral, we're getting a small number. Yeah, now the integral is only 0.01, right? And if you increase it even more, it gets smaller and smaller. And if you kind of imagine infinitely many squiggles, as was so eloquently put, then in the limit, it should be 0. So, so this is equal to the integral from minus pi to pi of sine of nx f of x dx, which hopefully this thing has infinitely many squiggles, inf squiggles. And hopefully that goes to 0. Okay, and we're going to actually prove this. Again, you could prove this kind of by hand, like trying to actually do the integral. But we're going to do it by thinking, only with norms and inner products. We're going to find a proof of this that just goes through like the functional analysis way of thinking of the functions as vectors and playing around with vectors and doing inequalities. So we're going to prove this without actually having to do this integral, which is amazing, because actually it's quite annoying. If you want to prove this by hand, you have to say like, oh, suppose f is like smooth and like approximated by its line, and then like do some integrals. Like it's a whole hassle to prove this by hand, but we're going to see a slick proof as we go, using the fact that these signs are actually orthogonal. And by the way, this inner product is also known as the Fourier coefficient. This is essentially the alpha n, is the nth Fourier coefficient. So we know that from our main quest in the course is to prove this Fourier thing. Yeah?
Just to clarify, so f of x here could be any function in L2, is that right?
Yes. Yeah. That's right. I will say, depending on what f you put in, you might need larger values of n, right? So if f has lots of squiggles itself, then you need some colossally huge n value. But for any fixed function f, eventually the n's overwhelm it. And you win. Yeah, so I picked one that was relatively tame in the picture to make things work. But it should work for any L2 function. Yeah, great point. Okay, so this is related exactly to our main quest in the course, because these are the Fourier coefficients, and the Fourier coefficients better go to 0 if we're going to sum them up, right? We're going to do an infinite sum involving the Fourier coefficients. We would be really screwed if they didn't go to 0. So the fact that these go to 0 is related to exactly what we want. Okay, so that is the sort of like motivation, I guess, for what we're doing today. And we're really going to formalize this idea, the ideas we've been trying to pursue in the course. So we're starting chapter 3.4, which is on orthogonal and orthonormal systems. Orthogonal and orthonormal systems. Okay, and we're going to start with definition 3.4.1, which says, what is an orthogonal system? Orthogonal system is a set S of vectors such that for all x, y, and s, so you pick any two vectors out of your bag of vectors, they are perpendicular. X is perpendicular to y. And the symbol means that the inner product of x and y equals 0. So we're working on an inner product space over here. And it's called orthonormal. Orthonormal if additionally, if also the norm of x equals 1 for all the x's in the S. So it's a big collection of things. In linear algebra class, you probably learned about an orthogonal basis. The reason we can't do that here is because we have no notion of a finite set. So in linear algebra class, it's a finite dimensional space, and you say the basis is the maximal spanning set and the minimal blah, blah, blah. We can't do that here because everything is infinite. And so it becomes quite tricky to say things. So that's why we use the word system to kind of be a little bit vague and just say some collection. You'll see sometimes people will write orthogonal sequence. Let's put this one down here as well. Orthogonal sequence. This means a system where they're in order. So they go 1, 2, 3, 4, 5, 6. If the bag of stuff you have is in order, then it's called a sequence. So x1, x2, x3, is the system S. And in our class, all the orthogonal systems will be actually orthogonal sequences. In an even more nasty class, you might have an uncountable set of orthogonal things or something. But in this class, they're in order. They go 1, 2, 3, 4. And the example is the one we just did. The example, the system sine of nx. So let's call that fn of x. The sine of x is an orthogonal sequence on L2 of minus pi to pi. And if you wanted to normalize it, you could do gn of x is 1 over square root of pi times the sine of nx. This is orthonormal. And you can always kind of normalize things by dividing by their norm. So it's really, for convenience, we work with orthonormal things. You could always just take any orthogonal thing and convert it to an orthonormal thing by dividing by some constant. That would just be like one extra step of work. Okay. Any questions or comments so far? So what we're going to try to do is we're going to try to prove that every orthogonal sequence is going weakly to 0, and that we can write, we're going to try to understand when is it that we can write any vector as a linear combination of the orthogonal sequence. That's what we're going to try to do. And to start with, we're going to prove a very useful theorem called Pythagoras. Theorem 3.2.14. You can tell your grandma that you learned about Pythagoras in your 4th year class. Okay. What does Pythagoras say? It says that if you have an orthonormal sequence, if x1, x2, are orthogonal sequence, then I'm going to write it like this. The norm of the sum of k equals 1 to n, and I'm not even going to put in coefficients, alpha k, xk, this norm squared. So you do some linear combination of some things in your system. Well, you could have done it like this. The sum from k equals 1 to n of alpha k squared, xk squared. So when you want to find the norm of something, if you write it as a linear combination of things from your orthogonal sequence, then you don't need to worry about anything other than the square of the coefficients. It all works out nicely. And I will put in, the proof is going to be by induction, and I'm going to use the baby version of of Pythagoras, which is that, okay, let's do it like this. So the proof, we're going to start with this baby Pythagoras, and we're going to use the baby Pythagoras to prove the real Pythagoras that we want. Pythagoras. And baby Pythagoras says if x is perp y, so if x and y are perpendicular, then x plus y squared equals x squared plus y squared. Okay. So if you have a right angle triangle, right, x plus y is like the hypotenuse. This is like the a squared. That's like the b squared. Let's draw the picture. X. Oh my goodness, you can't draw x as the vertical line. Okay, y, x, and then x plus y is this. X plus y. So the length of the purple hypotenuse is the square length is the y squared plus the x squared. Okay, and this one is a snap. Baby Pythagoras is really easy because the norm of x plus y squared is the inner product of x plus y, and now you expand. This is the norm. Okay, let's expand it properly. Okay, let's do it like this. X squared plus 2 xy plus y squared, and this middle term is 0 by x perp y. Okay, so it's equal to x squared plus y squared. Okay, so that one's a quick, easy proof. Basically, you know the inner product, you know the norms. Any questions about baby Pythagoras? Once you've proven baby Pythagoras, it's a quick, easy proof by induction to do this. So this is going to be the real Pythagoras. We're going to do induction on n. Induction on n. So suppose it holds for any combination of n vectors. So the statement was given, it depends on this value n, and we're going to suppose that it holds for size n, and we're going to prove it for size n plus 1. Okay, so notice that the sum from I equals 1 to n plus 1 of alpha I xi, you can write this as the sum of two things, 1 to n of alpha I xi plus the last term, alpha n xn. And not only that, if you call this thing y and this thing x, then notice these two things are perpendicular. X is perpendicular to y. Why is x perpendicular to y? Well, any sum of things that's perpendicular will still be perpendicular. Let's prove it. You can do the inner product. The sum of I equals 1 to n of alpha I xi with alpha n xn. This is what I'm calling, I guess I'm calling this yx. By linearity, you can pull all these things out. So it's the sum. Okay, this goes to, okay, I have an n problem. Let me fix my n problem. We're going to call this guy n plus 1, and then everything will be happy. Okay. So this is the sum from 1 to n of alpha I, and then you do the inner product of xi with xn plus 1, and you also have to multiply by alpha n plus 1 bar if you're doing it with complex numbers. So when you do the inner product of sum with the last term, that's the same as doing by linearity of the inner product. You can sum up the inner products of the individual things. But the inner products of the individual things are all 0, right? We were told it was an orthogonal system. These are all zeros. All 0 by orthogonal. Okay, so this big sum over here is perpendicular to that big sum. And now we can use baby Pythagoras. Baby Pythagoras says if you have a sum of two things and they're perpendicular, then you can do their norm. So therefore, by baby Pythagoras, the norm of the sum of the first n plus 1 things, alpha I xi squared, It's the norm of the first thing plus the norm of the second thing squared. Okay. This guy can simplify. If you're doing the norm of alpha n plus 1 squared, that comes out, right? That's just alpha n plus 1 squared, and then you have xn plus 1 norm squared. Very nice simplification there. What about this term? Well, by the induction hypothesis, we know what this is. This is the sum of alpha I squared times xi squared by induction hypothesis. Okay, and then depending on who taught you mathematical induction, you either have to write a sentence that says like, by the principle of mathematical induction, we've proven it, blah, blah, or you can just do 2 lines and say, I'm done. Okay. Questions or comments about this version of Pythagoras? Does it look like regular Pythagoras, or is it a different beast? People are nice. Some people are saying, come see, come saw. Okay. All right. So this is what I think of when I think of Pythagoras. Now I've been so long removed from ordinary Pythagoras. This is what I imagine. Okay. But now, okay, here is the thing. If you have Pythagoras, is you can start to prove really nice things. And the first thing we're going to prove, it's going to give us that result of weak convergence to 0 for any orthogonal system. It is called Bessel's inequality. So Bessel was some famous mathematician. You might have heard of the Bessel equation. I suppose he was French. I'm not sure. Bessel's inequality. Okay, and Bessel's inequality says you have x1 to xn, which are orthogonal. Orthogonal, or are they orthonormal? They're orthonormal. Okay, let's make them orthonormal. Orthonormal. So you have this orthonormal system. You have n orthonormal vectors, and x is any vector. Any vector. And really, we're doing kind of the first step towards writing x as a linear combination of the x1 to xn's. It's not going to be an equality, it's going to be an inequality. And Bessel's inequality says if you do x, you might think it's related to the sum from I equals 1 to n of x times xi times xi. So let's write it without a bar first. So let's write equals question mark. Okay, equals question mark. Let's write this first. If you're taking notes, you might need to erase the equals question mark later. So if you were in linear algebra class and you were working in an n-dimensional space, this would be an equal sign. This would say you write some vector x. How do you write it? Well, it's a linear combination of the basis elements, and the coefficient is the inner product between x and the thing, right? And you could prove this. You would say, well, it's a basis, so x equals the sum of alpha I times xi from I equals 1 to n. This is in linear algebra class. For some alpha I, that's what you would say. When we have a basis in linear algebra, we know there are some coefficients that work, for sure. And then you would say, what do the coefficients have to be? You would take the inner product of both sides with xk, and then you would discover that alpha I has to be x with xi. This is what we did on the first day of class. So that would be nice. And if we were in linear algebra class in an n-dimensional space, this would exactly be true. They would be equal. Unfortunately, we're in an infinite dimensional space. So they're not equal. They're not going to be equal. But what we are going to prove is we're going to kind of bound how far away they are. And to do that, we're going to take the difference and we're going to take the norm. Okay, and again, if we were in linear algebra class, the norm would just be 0, right? Because if they're equal and you subtract them, that would be 0. But of course, it won't be 0 for us, but it will be small. And what do I mean by small? It's less than something. It is small. Okay, I'm going to write it like this. It's equal to the norm of x minus, okay, with a squared, I believe. There's got to be a squared here. In my notes, it's not written with a squared, and I'm like very sure I just forgot in my notes. Okay, so I guess I've been using I everywhere. Let's stick to I. I equals 1 to n, and then you do xi squared. Okay? And this is less than 0. This is greater than x. Yeah, okay, and the norm of x squared is greater than this sum. Okay, so that's the theorem. So in linear algebra class, this is exactly 0. In our class, it's not exactly 0, but we can hope that it goes to 0, right? We're going to look at big sums, and we're going to try to prove that in the limit m goes to infinity, this is getting closer to 0. This last little statement, if you Google Bessel's inequality, that's what people use as Bessel's inequality. Of course, for us, the reason Bessel's inequality is true is the difference between this and this is the norm of some vector, and the norm of some vector is always greater than 0. So, by the way, this is always 0 is less than that norm. That's why the last little bit is true. But yeah, so the main statement is this part. Okay. Questions about the statement? That's what we're going to prove. I'm going to prove the thing in green. So this is approximating x by a basis. Okay, here's the proof. And I'm doing a proof that's slightly different than the textbook. The textbook proof is one of these really terse proofs where I don't understand anything. So I made up my own proof. Of course, keep an eye out because maybe I flubbed something and it's totally wrong. Okay, so here's the claim. Claim. We're going to make a vector called Vn. Let Vn equal, what is Vn? It's going to be x minus the sum from k equals 1 to n of xk times xk. Okay, that's the vector that we're taking the thing of, right? So this is exactly the vector that appears here. If I had defined it first, I could have just written that there, but that's Vn. And the claim is Vn is perpendicular to xk for all 1 lesser equal k lesser equal to n. So Vn is some vector, and I'm claiming it's perpendicular to all the vectors in the list you gave me. Another way to say it is we have our system with x1 to xn, and I've tacked on one extra vector, this vector Vn, and that one is perpendicular to everything. I've enlarged my system by one extra vector. Here's the proof. It's a very nice proof. You just calculate. So let's do the inner product with Vn with xk. And what is it? Well, it's this inner product. Okay, this is where you have to be careful with your dummy variables and your variables. So here I have a sum with k, and here I have xk. But this k and that k mean different things, right? This k over here is a dummy variable. You can replace that with any letter, and it wouldn't change anything. Whereas this xk is like the k we're proving it for. So to not get confused, why don't we change this back to an I, like it was originally? And then I think things will be a little more clear. This is like a skill you learn, is to be careful with your dummy variables so you don't get mixed up on what is what. Okay. But that is what I have. And I'm going to expand this out. There's two parts to this. There's x, xk. There's a minus, there's a sum. And then there's the coefficient xxi. And then you have xi, xk. This is the kind of sum you'll see all the time in like physics classes, things like that. All right, the first one is xxk. The second sum simplifies dramatically. And so what you have to be able to do is look at this and understand how to simplify it dramatically. And this is where, if I had used I instead of k, you would just like lose your mind and like have no chance of saving this. But as written, k is the fixed thing. So for k fixed, I is this dummy variable. Does anyone see how to simplify this? Yeah.
Well, they're coming from an orthogonal system, so that's always your selection 0.
They're all 0, is that what you're saying?
Yeah.
Yes, okay, great. So they're all 0, right? Xi, xk equals 0 because it's an orthogonal system. I'll say orthog system. Wonderful. So actually, it's a big sum, but actually every single term is 0. Okay, great. So this is x, xk minus 0. You sum up n copies of 0, you get 0. Wonderful. Okay, so the answer is x, xk. which is exactly what we wanted. We wanted to prove that Vn xk was, we wanted to prove they were perpendicular, and then we did the inner product, and we came out with a number that is not 0. So there's a mistake.
Wouldn't the sum not be 0 when xi is xk?
Very good. So they are orthogonal, and it's very tempting to say this kind of thing, right? If you have an orthogonal system, any 2 vectors from it will be 0. Of course, that's any 2 that are not the same vector twice. If you give me the same vector twice, of course it won't be 0. So actually, this sum is mostly zeros. There is one term that is not 0, and that is the term when I equals k. So you could write this minus, there's one more thing, which is when I equals k, and in that case you have xi times xi xk, and sometimes in physics class you'll see this, they'll write the Dirac delta, or the Kronecker delta, delta ik. I'm not going to write delta ik because it's scary, so let's banish delta ik. But it just means when I equals k, something different happens. When I is not equal to k, it's all 0. When I equals k, we have a different thing. And in that case, we have xi with xk, but of course I equals k. So it's the same thing twice. That is just the norm squared of xk. Okay, and you also have, you might as well replace the I with a k. Okay, so you have xxk on the front, but then you have xxk again. And now, not only was it an orthogonal system, we said it was an orthonormal system. Hopefully I wrote that. Yes, good. Orthonormal system. So not only is it orthogonal, it's orthonormal. So the norm of xk squared equals 1 by normal. And so you actually subtract off xk times 1. And now it does work exactly as we wanted. The thing that was on the front before is exactly subtracted from the other thing. This is 0. And of course, it is completely cooked up to make this work, right? Like, the reason we put the coefficients in there was exactly to make this kind of calculation work. So Vn, this guy, is perpendicular to all the xk's. Questions or comments about this proof? This is a very common proof if you work with these kinds of things with vectors. You might have seen this in linear algebra class before. Okay, now that we know this thing, the proof of Bessel's inequality is just Pythagoras. And it's a very sneaky way. We're going to do everyone's favorite math move of adding and subtracting 0. So x is the vector we're working on. You can write x as a sum of 2 things. You can write it as x minus the sum from k equals 1 to n of xk times xk plus the sum from k equals 1 to n of xk times xk. Right? Seems like I've done nothing. But actually, this is a huge convenience because this is what we call Vn, and this is x1 to xn. And x1 to xn and Vn are all perpendicular to each other. The x1 and the xn's are all perpendicular. Vn is perpendicular to any of these. That's what we just proved. So this is a sum of things where every single term is perpendicular to every other term. There's n plus 1 terms in the sum. There's the first term, and there's the other n terms. And they're all perpendicular to each other. And now we can just apply Pythagoras. So by Pythagoras, by Pythag, if you do the norm of x squared, well, if you do the norm of x squared, and x is a sum of perpendicular things, then on the right-hand side, you just have the perpendicular things. K equals 1 to n, xk times xk, norm squared. And then over here, you have k equals 1 to n, xk. The norm of xk squared is 1. Maybe I'll write down as one more step. Like that. So that's Pythagoras applied to it. I'm missing the squared, which is right here. And one more step. Copy it out. Okay, let's not do one more step. Let me just cross out this thing and write 1. This thing is equal to 1. So there you go. And that's exactly what we wanted to show. So the norm of x can be written as a sum of 2 vectors, and because this thing is just the sum of the inner products xk squared. That's exactly what we wanted to show. And therefore, this is the thing that people use sometimes, is that this is always greater than 0, because it's the norm of something squared. So the classical form is to say that the norm of x squared is greater than this sum, k equals 1 to n of xk squared. Okay. This is Bessel's inequality. So some people call this Bessel's equality, this line, and some people call this one the inequality. This is the inequality, inic, and this is the ek, the equality. Okay. All right. Questions or comments about that one? Seems a little mundane, but we're going to see that this equality is exactly the kind of thing we need to do. Because if you start taking limits as n goes to infinity, you can ask in the limit as n goes to infinity, does this converge to that, right? This is going to be increasing as you add more and more terms. This can only go up. And it can either go up all the way to the norm of x squared, or it can go up like halfway or something. And we'll see that that is exactly the question that we need to answer. All right, so here is the first statement answering the warm-up problem today. And in the textbook, they do this, and they don't give it a name. So I'm going to call this the unnumbered proposition from the textbook. And you have to find it somewhere in the pages near where we're working. Unnumbered proposition, which is if x1, x2, ... are an orthogonal sequence, then xn goes weakly to 0. And this answers the question we had about sine of nx, right? So sine of nx was an orthogonal sequence, and it goes weakly to 0. Why is that true? Here is the proof. The proof. For any x, we know the norm of x squared is greater than the sum from k equals 1 to n of xk squared by Bessel, inequality. And therefore, taking the limit as n goes to infinity, take n to infinity, the norm of x squared is greater than the limit as n goes to infinity of k equals 1 to n of xk, all squared. And if this limit exists, this limit is increasing and it's bounded above, and therefore it exists. That's the monotone convergence theorem for real value numbers. But in any case, these numbers better go to 0. If they didn't go to 0, then this thing would explode to infinity, and it wouldn't be bounded. So therefore, since right-hand side is bounded, therefore, the limit as k goes to infinity of xk all squared equals 0, right? If the terms didn't go to 0, then definitely the whole sum would blow up. So it's actually even stronger than the terms going to 0. Not only do they go to 0, they're actually summable, but we just need that they go to 0 for weak convergence. So this answers the question about the sine of nx without having to worry about squiggles, right? Like we answered the question, we didn't mention squiggles once. So just by thinking about like linear algebra, essentially, think of your functions as linear algebra, you get the answer. Okay. Also, they do go weakly to 0. Note that they definitely don't go strongly to 0 because they're always norm 1, right? They always have constant norm. So this is a nice example of orthogonal sequences. Okay, yeah, questions about this? We're about to introduce something that's important. Okay, here's the next definition that you must know, and probably has been mentioned already. And I've diverted this definition for quite some time, but the definition of a Hilbert space means inner product space that is complete. Inner product space that is complete. Complete. And complete means every Cauchy sequence converges. I don't know if we've done this one already. Every Cauchy sequence. Okay, great. We're about to use it. So up until now, it's been a curiosity. Like, who cares if it's complete or not, right? But now is the moment that it matters that it's complete. And we've proven, for example, that the space capital L2 is complete. That was all the work we did with the stupid Lebesgue integration of the step functions and all that. It was really to prove that it was complete. It is complete. And here is the fact. This is the fact. And again, it's another unnumbered proposition, right? Unnumbered fact. Unnumbered fact in the textbook. Numbered fact. If x1, x2, dot, dot, dot is an orthogonal sequence, let's say orthonormal. Actually, that'll make things nicer. Orthonormal sequence. Then the limit as n goes to infinity of this sum, k equals 1 to n of x, xk, xk, converges to something. To something. This is, let's say, in a Hilbert space. In a Hilbert. Okay. Why does it converge to something? Well, the proof is very simple. Since it's absolutely summable. So the norm from k equals 1 to n of x, xk, xk, this is equal to the sum from k equals 1 to n of x, xk squared. That's Pythagoras. So this sequence of vectors, if you take its norm, then you get exactly this. And by Bessel's inequality, this is less than or equal to x. And so because this thing doesn't blow up, it's absolutely summable. It's converging. The norms are converging as a sequence in R, and that means it's an absolutely summable sequence. And in a Hilbert space, every absolutely convergent sequence converges to something. Every absolutely summable sequence is also Cauchy. All the Cauchy sequences converge. So this thing, we've proven it can't blow up in norm, and therefore it has to converge to something in the Hilbert space. If you weren't in a Hilbert space, it could be that it's always bounded, but it kind of like goes to some weird point that doesn't exist in the space, like in the rationals. But if you have no holes in your space, then it's got to be something. Okay? So it converges to something. And now we're oh so close to proving our Fourier series thing, right? Because if this converges back to the original point x, that's exactly what we want. That's writing x as an infinite sum. So this thing converges to something. If the something is equal to the original thing we started with, the original x, then we're happy. And we give this a name. Let me give this a name. And this is the big definition of the day, which is what is a complete orthogonal sequence. Definition 3.4.12, which is a complete orthogonal system, or let's say sequence. And again, you have to be careful because the word complete orthogonal sequence, the complete is related to, but it's not exactly the same as complete, like every Cauchy sequence converges. So watch out. But the definition is x1, x2, dot, 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 is a complete orthogonal sequence. Means for all x, x equals the limit as n goes to infinity of the sum k equals 1 to n of x, xk with xk. So we know that this always converges to something. If the something that it converges to is the original thing you started with, then it's a complete sequence. So the whole sequence together is big enough that it gives back every vector x. All right, let's do an example. Actually, this is a great mathematized question. I'll make it a mathematized question. Is the sequence sine of nx complete? And to make it orthonormal, let's divide by this. That's what we started with. 1 over square root of pi sine of nx. I haven't actually made this a mathematized question, but I'm going to do it right now. So you guys start thinking, take 2 minutes and think, do you think this one's going to be complete or not? So it's an orthonormal sequence. Is it complete? You decide. Okay, I'm going to make this a question, and then you guys will answer it. The question is almost done being created. Okay.
Oh.
Why did it tell me that it's
Okay.
Why is it telling me it's not having similarity or something?
Okay, here we go. It's live. There it is. Is it complete or not complete? Sine of nx.
Now I'm curious. Well, should we get transfer of the cosecant? With that,
Okay, yeah, great. This is perfect.
It turns out Bessel is German.
Bessel's German, he's not French.
No.
I insulted all the Germans, sorry.
From Alsace.
Yeah, okay.
Okay, good.
Thanks for looking it up.
No, he's from Königsberg. Says Königsberg, yeah. So I guess he's Russian.
Doesn't that not exist?
It's Kaliningrad nowadays, so it is Russian. So
Yes.
I guess. Well, technically he's Russian.
It's Russian.
Yeah.
It's like.
Oh. Germany did
I
all
thought you were
Königsberg.
No, but it's all like.
But he was born in Russian, so he's definitely Russian.
It's supposed to be the hard shell that came up to.
No, sorry, he was born in Minden. He died in Königsberg. Where's Minden?
Yeah, completely shattered.
North Rhine
That's more
Westphalia.
good, I think.
North Germany, never mind. No, Minden is a middle-sized town in the Werderfries of North Rhine-Westphalia, Germany. The largest town in the population between Bielefeld and Hanover. Bielefeld doesn't exist, so.
That's stupid.
Okay, good. We got a nice little history lesson on Monsieur Bessel. Or I guess it's Herr Bessel? Okay, yes.
Hey.
My-
Anybody know where Herman is? But wait, if Bielefeld doesn't exist, which city is Minden between? Really different way. Does any course actually go over information?
Oh, we had 12 people when the class started. Now there's only 11 people. Someone stuck out. Okay, there.
No, that's their.
Well, I mean, part of the reason to do the question is to give you a little break of not having too much math all at once. Okay, we're up to 12 people. Let's see what you guys think. Is it a complete orthonormal sequence or not? People said
Maybe.
reveal counts. Ooh, 7 to 5.
Ooh.
Pretty close. As usual, my favorite thing in the world. Debate, and we will arrive at the truth of the matter. Okay, so I'll let you chat, discuss. About half of you think it's complete, about half of you think it's not complete. Come up with a compelling argument. Okay, I'll let you revote.
I think it is match. Here's the trick. There is no way. Well, okay, wait, let me ask something. Is
Yeah.
the index beginning at 1?
Oh, yes, we'll start at 1.
We'll start at 1.
Yes.
So there is no variable. You can multiply the sign. So because the sign there, that sign is 0 at minus 5.
Yeah, the same thing with the closest.
Which means there is no
It's like
constant you
the-
can multiply any of those functions by.
8
To get a null, to get a value which is not zero.
Right, so like if you had like.
So for example,
Yeah,
if
function the other way of not zero.
Yeah, so like
If the
cos.
base is
cosine. You cannot do the cosine because there will always be any sum of those has to be 0 and minus 5
those
divided by.
kind of.
So it's
might
fine.
be related to this, which is about
For all.
how like.
Watch me be wrong.
The 48 series would be the sine and cosine, and I feel like I'm using the cosine.
Yeah.
In our definition, is it for all x and h?
For all x and h. Okay, that's right.
Oh, go ahead and space H.
Hilbert.
Yes, for all x. Yeah.
It's like I.
What's his name? No, that's called Banach spaces H and Hilbert spaces B. Because that'll be funny.
Okay, let's put a timer on the thing. Let's go for 2 more minutes. Oh, you guys aren't talking very much. Let's just. Okay.
Oh, there's well, I don't think A0.
I would agree. That was the first thing I thought of, was how do you get coast out of it? But maybe you can. But the Fourier series focuses on with the coefficient, right? So I'm thinking
Oh,
maybe
that's
science
nice.
is not.
Ooh, yeah, that's. Yeah. I think Corsican doesn't have a Fourier series. It might have actually. I think it's a bit bold. No, it doesn't.
But cos of 0 is 1. So you're
Which one? I was gonna ask. Yeah, it can't be like represented by Fourier from scale. L2. That's what. I think it's just L2.
Okay, put in your final answer.
The final ending. No.
This does not converge to each other.
Okay, let's see what you guys said. In the second round of voting, 10 people are now in it's not complete, so lots of switching. And the correct answer is it's not complete. So you guys figured it out. Very good.
How do you say correct?
Does anyone have a simple reason that shows why it's not complete? Yeah.
If you think about it, those signs are always going to be 0 and minus pi, 0 and pi. So if that's
okay,
not
great.
0 there, you can't sum the pi.
Okay, this is a fantastic argument worth writing down. So here is what you're saying. You're saying at x equals 0 and x equals pi, and I guess and minus pi,
Yeah.
and x equals minus pi, sine of nx equals 0. And so you have these functions, and they have these points where they're always 0. And then you're like, well, now you have the function. There's no way you can write a function that is non-zero at these points as a linear combination of things that are 0, right? Therefore, f of, let's do pi. F of pi is not equal to the sum of k equals 1 to n of alpha k times the sine of n pi. So I plugged in x equals pi to make things concrete when f is non-zero at pi. So this is a totally true statement about the point f of pi. However, I just want to point out what we are talking about is not f of pi. We're talking about f equals the sum from k equals 1 to n of alpha k sine of, I'm gonna call it n dot. We're talking about them as functions in L2. We're thinking of them as vectors in L2, and we're thinking of, is this thing equal to that thing as a thing in L2?
So you're talking like almost everywhere.
So this is the problem with your argument. The argument you said is not correct because in capital L2, do you guys remember the stupid thing about script L2? Right? When you have convergence in L2, that does not mean that it converges at every point. So it could be that this is true, the second line. It could be that this is true, could be, even if it doesn't work at some points. So if you have a handful of points where the convergence doesn't work, that does not stop the capital L2 convergence. So knowing that it doesn't work at the points pi, 0, and minus pi is not enough to preclude L2 convergence.
So are we in script though? Or like
Well, okay, what we really want is this limit, right?
Yeah.
I wrote it like this. This is all in H. So I want this x as a vector to be the limit of this thing in H. That means with respect to the norm. So in L2, we really mean it with respect to the L2 norm. And so you cannot look at points. Looking at points is not enough. Of course, the other way can be true. But yeah, okay. So this argument is not correct. This is not correct. So it's true that it's not complete. And this is a really common misconception. And in fact, when we prove our Fourier series, the Fourier series will only converge in L2. And you can strengthen it, but it does not converge at every single point. So Fourier series don't converge everywhere. They converge almost everywhere, unfortunately. Yes. Okay, very good. Okay, this is a fantastic misconception we've cleared up. Does anyone have a different argument of why? Yeah.
You said this to me, and
Okay.
I think it works. I think the product of cos with sine nx is 0 for all.
Okay, so you think, so the new idea, let's look at the function cosine of x, and you want to do the inner product of cosine of x with sine of nx. Okay. And it does turn out that this one is 0. So this is one we did, again, we did it a long time ago. Sine of nx goes up and down, cosine of nx goes up and down, and they kind of go up and down out of sync. And when you integrate, when you add up the greens and the reds, it will always be 0. Let's do it quickly because we have the Desmos open. We can quickly check. So we did this function, which was some complicated function. What happens if we put in f is the cosine function? Let's see what happens. So cosine of x, and so it's going to look like this. Let's zoom in a bit. I think I can.
You can press the home button.
Okay, so, and let's go down here. So the purple function is the cosine function. When you have sine of 2x, you have 2 reds and 2 greens. They perfectly cancel. What about sine of 3x? Sine of 3x. Okay, now it's more complicated, but can you see the symmetry, right? You have a little green and a little red. Big green, big red. Perfectly cancels. And in fact, if we go down to the integral, it's always 0. 0. And we can go through all of them. The integral is always 0, no matter what. There's some symmetry going on where the positive parts and the negative parts always perfectly cancel. So this thing is 0. Okay. All right. I grant you that this is 0. So what? Why is this a problem? Who cares? Why does it matter? Yeah.
If you sum up 0 times the sine nx's,
Yeah.
you're summing zeros which don't add to the cos function.
Very nice. Okay, so these numbers are 0, and therefore the sum of the first n terms of cosine of x times the sine of nx of sine of nx, this will be the 0 function. 0 function. Because you added up a 0 coefficient times the sine. So when you do the first n terms, you add them up, you get 0 plus 0 plus 0. They're all 0, and when you add them up, it's just 0. And there's no way, if you do the limit of the zeros, therefore the limit, as n goes to infinity, of the sum, let me not write it again, equals 0. And that is not cosine. That is not cosine. And it's important, the cosine function is not equal to 0 almost everywhere. So we're not just looking at a point, we're looking at the entire function in L2, and they're different. You have basically just discovered this idea is the proof of the next theorem. So theorem 3.4.14. An orthonormal sequence is complete. Orthonormal sequence is complete if xn equals 0 for all n implies x equals 0. Let me write 0 vector in H. So equals 0, this is in R. So the only vector that is perpendicular to everything is the 0 vector. If that's true, then it's complete. And actually, this is an if and only if. This is the exciting thing. So we've basically proven one direction, but it's if and only if, and only if. So this is how you check if something is complete. You check, is the only thing that's perpendicular to everything on the list that I have the 0 vector? If that's true, then it's complete. And we've proven one direction. So one direction, this is the implies direction. So proof implies. So suppose xn equals 0 for all n, then the sum from k equals 1 to n of xk times xk equals 0 for all n, and therefore the limit as n goes to infinity of xk is also 0, and this is in H. So if it's 0 for every single thing, then you do the sum, you get the 0 vector. And if it was a complete sequence, since xn is complete, therefore x is equal to the limit as n goes to infinity of the sum k equals 1 to n of xk, which is 0. So this is showing if you have something where the inner product is always 0 in a complete sequence, then the only vector that could have that possible property is the 0 vector itself. That's the proof we just did. But the interesting thing is it works in reverse. So the reverse is true. If you have something whose limit is 0 like this, then it must be that xn equals 0 for all n. Is that what I'm saying? No, I have it totally backwards. I'm saying, okay, we're doing this arrow. We're doing this if and only if. So on one side it's complete, and on the other side we have this property. And we've just proven if it's complete, then this property is true. Now we're going to prove the reverse, that if the property that is circled in the big orange circle is true, then it's complete. That's what we're going to prove now. All right, I went maybe a little fast. Any questions or comments about where we are? Where the if and only if lives? Yeah.
Can you say that one more time? What we just did?
Yes. Okay. So great. So there's two properties. One is you have some sequence, and it's either complete or not. And then 2 is the sequence either satisfies this property or not, right? And we have proven that if it's complete, then it satisfies the property. We've proven blue square implies orange circle. Now we're going to do the reverse. That orange circle implies blue square. The one we just proved is why the sign of nx could not possibly be complete, because it failed this property, right? So because it didn't have the orange circle property, it was definitely not complete. It was a counterexample situation. And now we're going to show that if we can check that we have a sequence that is perpendicular to everything, then that sequence would be a complete sequence. All right. Other questions? Okay, let's do it. And again, it goes through the vector that I called Vn from before, right? No, it doesn't. Okay. Okay, this is how it starts. And it's important we're in a Hilbert space. By the unnumbered Hilbert space theorem, numbered Hilbert space theorem, there exists some y such that y is the limit in the Hilbert space as n goes to infinity of the sum from k equals 1 to n of xk with xk. So in a Hilbert space, this thing is always converging to something. We're going to call that something y. And we're going to show that when you have this property, if the orange property holds, y is going to actually be equal to x. We're going to prove that y is equal to x. Okay, so we want to show y equals x. If y equals x, then that means it's complete space. Okay, how are we going to prove that y equals x? Well, we'll prove y minus x equals 0. Okay, if y minus x equals 0, then y equals x. Very nice. How are we going to prove that y minus x equals 0? Well, we know that the thing in orange is true. So why don't we prove that y minus x inner product with xn is always 0? Because then, by the hypothesis, then y minus x will be the 0 vector. So we will actually show, we'll prove y minus x xn equals 0 in R for all n. And then by the hypothesis, y minus x equals 0 holds. Okay, let's prove that the inner product of y minus x with xn equals 0. What is the inner product of y minus x with xn? Well, y minus x with xn for some fixed n. Y is a limit. Y is the limit as k goes to infinity of the sum from k equals 1 to n. Okay, k goes to infinity. I'm going to sum I going from 1 to k of xi minus x, all with xn. Okay, I'm going to do this limit. And that limit holds in the Hilbert space H. So this is the moment where you need to know that when you do a limit inside an inner product, it's okay to pull the limit outside, right? Sort of like inner products are continuous. You can prove this by Cauchy-Schwarz or something. So this is equal to the limit as k goes to infinity of the sum I equals 1 to k of x, xi. Let's do it. Let's just do one step at a time here. Let's do it like that. So if you have a limit of vectors inside an inner product, you can do the limit on the outside and do a limit of numbers. Okay. Okay. This inner product I can split up again. The limit as k goes to infinity. You have the sum I equals 1 to k of x, xi with xn. And then you have minus x, xn as a separate thing. This is the same exact kind of inner product we did before, where we said things are all 0, right? It's very tempting to look at this thing and say, xi with xn, hey, it's an orthogonal system that's always 0. But it's not always 0. It's always 0 with one exception. And the exception is when I equals n. So this whole thing equals 0 unless I equals n. So it's going to be a lot of zeros until I equals n. Notice that if k is less than n, then that never happens. So you have to be careful here. If k is less than n, that never happens. But we're doing the limit as k goes to infinity. So eventually, k is bigger than n. And once k is bigger than n, we have a bunch of zeros here and exactly 1, 1. So the way I would write this, I would say that this thing is equal to the limit as k goes to infinity. And this thing is equal to the inner product of x with xn. And then you have the norm of xn squared. And then I would write as long as k is bigger than n, right? If you want it to be perfectly precise, you could say it's this when k is bigger than n, it's 0 if k is less than n. But the only fact we need is that it's that when k is bigger than n. And we're subtracting x with xn. It's an orthonormal system, so this thing is equal to 1. The norm of xn squared equals 1. So as soon as k is bigger than n, this whole thing cancels and we get 0. If that works whenever k is bigger than n, then certainly in the limit as k goes to infinity, it's just always 0. So this thing equals 0. The limit is 0. And because the limit is 0, that means the original inner product we were looking at is 0, and therefore the inner product x minus y with xn equals 0, and therefore x minus y is the 0 vector by hypothesis, and therefore x equals y. Okay. Was there a question here? Yeah.
How do we do the second last step? Yeah, the one with the yellow highlight.
This one?
Yeah.
This is the same trick as we did earlier, which is x, x1, x2, x3, all the way up to xn, all the way up to infinity. They're an orthogonal system. So the inner product of any two vectors is 0, right? So this thing is very tempting to say this is just always 0, and that's almost exactly true. They're always 0 unless I equals n. And when I equals n, you just have xi with xn, but I equals n. So that's xn with xn, which is the norm of xn squared. Yeah. So this is the same trick as we used earlier when we did the vn, all the way back over here, right? The exact same trick as this guy, xi with xn. Yeah. So if I was a physicist, I would write this Kronecker delta on the board, but I won't do that. Okay. All right. Great question. Anyone else? Yeah.
What was the bit you said about being able to pull out limits of inner products?
Okay, yes. So the limit is super overloaded in this course, right? Because we have limits in R, like you did in previous courses, and then the new thing in this course was limits in the vector space. And whenever we write limit, you have to look at what the limit is. So for example, this limit over here in green, that is a limit of a sequence of vectors. We're adding up the vectors I equals 1 to k, that's some vector. We take the limit as k goes to infinity, that's a sequence of vectors, and we know it's converging to something. That was, because we're in a Hilbert space, that was this limit. Right? So this is in H. But on the other hand, on the next line, In orange over here, I wrote limit again, but that is not the same type of limit. Now it's a limit of numbers. And that's because everything over here on this thing is those are the sequence of numbers. And so I've replaced a limit of a sequence of vectors with a limit of a sequence of numbers. Why is that okay? Well, you would have to prove it, and the way you prove it is by Cauchy-Schwarz. I think you did this, or we did this at some point. So I guess the fact that I'm using, fact. If let's give them a different name. If yn, okay, if zn converges to zn converges to z, then the inner product of zn, say w, converges to zw. Yeah, okay, we did this the day after the midterm because the proof is very similar to problem 1 on the midterm. So we did it as a little bit of a review of that one. And the proof is by Cauchy-Schwarz, right? The inner product of z and w, if zn is really close to z, then the inner product of z and w is really close to the inner product of zw by Cauchy-Schwarz. So that's what we're using here. You're replacing a limit of vectors with a limit of numbers. Fantastic question. Yeah.
So is the limit in green here is with respect to the norm that's induced by the inner product?
Correct, yes, exactly. That's right. Right. Okay. So now we know what it means to be complete. We know that these complete sequences recover the original things. The only thing we have left to prove is that the signs on their own were not complete, but the signs plus the cosines together, that is complete. And we're going to prove that in the next few classes. Starting next Thursday, we're going to start having presentations for the final project. So make sure you check that out. I posted some more details. Feel free to contact me as well. But it is important you know when you're presenting. So go check in the gradebook. It'll tell you when you're presenting. I think everybody got their first choice who submitted a thing. So you shouldn't be too surprised with your date. But do double check. Okay, yeah, let me know if you have any questions. I'll be here for a bit if you want to chat. And
What should we submit for the final draft?
what should you submit? So it can be like the article that you're writing. And it doesn't need to be, so for the draft, it doesn't need to be complete. Like, basically you get just marks for completion. Like if you did some stuff and I can give you some meaningful feedback, then you get the full 5 marks for that. So it doesn't need to be like fully nicely done, but the point is to give you lots of time to get some feedback and then fix it before the final submission. Yeah. Okay. So there is some like information on due dates and stuff that's posted on course links. So go check that out if you haven't seen it yet. Okay.
Okay. Yeah.
I'll stop there.